So I would like to start out by thanking my co-authors, because this has been a team effort with several people involved and several research questions that what we are asking here. And we are presenting today mostly the radar interferometry results that we have achieved. So my co-author Manfred Strecker and Peter Omendo, we have been doing fieldwork, field mapping in this area, including working with LiDAR data. And I would specifically like to acknowledge the CanGen geology team that helps us setting up the GNSS network that we established at that local sites in Olkaria. And what you see here on the title slide is already a view of some of the geothermal sites that extract water vapor from the ground, of course, heated water vapor that is being used for energy generation. Let me move on to the study area. We already have seen two great introductions to that larger area. So we are located here in the rift area, and we are going to zoom in to this area that includes Nairobi and then the Olkaria geothermal field, as we call it. The the geothermal field area here indicated by this red star. This black dot is Nairobi. And on the eastern escarpment, we have the Mau escarpment. On the western side, we have the Kinangop Plateau here, and then the Aberdare escarpment located here. And in that vicinity of the Olkaria geothermal field, we have the Longonot volcano that is right here. And we have Suswa that we heard about from Kyle that has seen an inflation event in 2019. Let me just give you some background information on the Olkaria geothermal field, because that's important to understand the energy generation that exists in this area. So the OGF is underlined by a fractured volcanic reservoir. This is mostly of tectonic origin, the fractionation, because you can see in this zoom in area here that the rift is taking a turn. So we have a transfer zone that is certainly causing a lot of additional deformation in this area. The water that is being produced or recycled in here is to 50% roughly from Lake Navasha, and the other half is deep-seated groundwater. The Maui escarpment goes down to 2.5 kilometers depth. And that helps us recycling some of the water and bringing it back up. The data that I'm going to look at today is mostly Sentinel-1 data. So I'm going to use a time series that goes from November 2015 to May 2025. This is very similar to the data that Kyle has been presenting in the first talk. I'm also adding the descending track. It's a shorter time series because there were too many interruptions in that track, but it helps us to understand the general setting. And I'm zooming into this white area here, which is an area where I use a different technique of radar interferometry using persistent scatterers to really zoom in and get the highest resolution results. This is computative very intensive, and that's why I'm limiting it to a smaller area. We are using the high performance computing cluster at the University of Potsdam, and even using that, it takes some time to get these data processed. In addition to the Sentinel-1 time series, we are cooperating with the DLR, the German science, or the German NASA in that sense, and we are using TerraSAR X and TandemX data as well to better understand the very detailed deformation of this area. Let me just say a few words about the OGF, and that partly motivates some of the presentation today, and that is that the Olkaria geothermal field is the has the longest and most prolific history in Africa. It started in 2050, and the electricity generation began in the 1980s. That's the Olkaria 1. And then the production capacity was originally 15 megawatts in 1981 and had been increased by more than an order of magnitude with the last Olkaria 6 that has been started in 2022. What has been noted is that already in the early 2000s is that there's a pressure decline of 10 to 15 bars, which is averaging to roughly 1 to 2 bars per year of the fluids that are being extracted from this area. And that caused concern. That caused concern in the sense of that, is that system sustainable? That question has been addressed in previous publications. I'm listing some of them here, but I also wanted to point out that 2 recent publications, and I'm mentioning here Albino and Bix. They have identified that line of sight descending signal, the subsidence signal, and also the presentation from Kyle. He has worked on this as well, and they are suggesting a rapid subsidence rate. And I'm going to look at that in detail with different data, and I'm going to start out by showing you some of the high resolution areas or results for only this area. So what we have is the Lake Naivasha here. We have Nairobi down here, where you see the strong subsidence signal that we saw earlier. And everything that you see on this map is relative to this black cross. This black cross here is a base GNSS station that we set up that serves out at our reference frame. So if you see red colors here that have negative values, it means in relation to this black cross at the shore of the Lake Naivasha, this area is going down. So we have the Olkaria geothermal field, we have Longonaut, and we have Suswa here. This is the descending view, and you have a similar signal. You have subsidence in the Olkaria geothermal field. You see uplift in the Suswa region, and that is the geothermal inflation event that we heard before. And this is a shorter time series, so this is why this signal is popping up. So from this general overview, I would like to mention that we are using a high multi-looking approach, roughly the equivalent of 200 meters to get rid of vegetation disturbances. We have been hearing this before. This is one of the major sources of errors that we have. We can create higher resolution data at the equivalent of 30 meter, but that would definitely decrease data quality. So zooming in, this is what the general distributed scatter approach looks like. So again, everything is relative to our GNSS station at the Kengen site. We see subsidence in Olkaria. We see some local dots that show higher subsidence rates, and these are dots that I would like to focus on, but I'm going to show you a different data set, and the different data set that I'm using a persistent scatter approach. So instead of averaging over a larger area and trying to remove the vegetation component or other disturbances, I'm saying just give me the points that are really, really, really reflective. So for example, bare rock outcrops, the roofs of buildings, anything that is not changing and is stable through time is producing a persistent scatterer in the radar signal with respect to that wavelength, and that allows us to perform a calculation of a much more detailed and higher spatial resolution data. So this is showing you here the Olkaria geothermal field, and you can now clearly appreciate that there are some red dots, and those red dots are subsiding very, very rapidly, and those red dots coincide with the pumping sites or the extraction sites of the energy production that occurs in Olkaria. And what I'm going to do next is I'm going to zoom in one of these dots. I chose this dot because it is the largest and brightest one. And I'm going to show you a time series. So the time series that I'm showing you here is starting in 2016, is going to 2025 in May. So I processed the data pretty much up to last month. And you are seeing two curves here. One curve in orange is is the standard distributed scatterer approach that you produce through multi-looking. But we know that there are some problems with this in areas with either great or high soil moisture or vegetation cover. So instead of focusing on that orange curve, the multi-looking curve, I would like to point out the black curve, which is a persistent scatterer curve. They overlap in the beginning, but then they start to diverge, suggesting that there may be some bias in the curve. If we are performing linear regressions in 3-year steps, we see that we have a subsidence fairly rapidly between 2016 and 2021, but then starting in 2021 or maybe 2022, it's slowing down. So we don't see that same rapid subsidence. In order to verify this signal, I have converted the line of sight deformation to a vertical displacement by using the GNSS data, and I'm showing you the ascending and descending data. So I'm showing you the shorter time series of descending, this is this blue line, and then I'm showing you the rate of the ascending data, and they both agree very well. So the rates that we are deriving is roughly on the order of 35 to 40 millimeters per year subsidence. That's pretty rapid for an area like this. So, when we look at this and we have discussed it, we were wondering what are points doing outside of those construction sites, out of those water extraction sites. So what if we look at an area that is within the Olkaria geothermal field, but not at a water pump or at an extraction site? And what you see here is this blue line. This blue line is indicating I call it the background rate. It is located on the Olkaria geothermal field, but it's not anywhere close to a geothermal station. So we see that both areas are subsiding, but then in 2019, 2020, things started to diverge a little. There may be a spatial factor in there too. We know that the deformation in volcanic areas can be fairly localized based on the subsurface structures that exist. But what I would like to do as a kind of a summary figure is to look across the Olkaria geothermal field, showing a profile and showing it as a time series. So what I'm showing here is a profile from the shore of Lake Navasha across the Olkaria geothermal field. And each of those lines are presenting the subsidence at a specific year. So I averaged all measurements for 2016, 17, 18, 19, and 20. So we can clearly appreciate that in the center of the geothermal field, we have stronger subsidence, but we also see subsidence at the shores or at outside the Olkaria geothermal field area. So this is what is happening in the first 5 years of the data, so from 2016 to 2021. And now if we look at the last 5 years, from 2021 to 2025, we see that subsidence signal is not continuing. It's more or less stagnating at a larger spatial area, so that the rapid subsidence that we observed in the first 5 years of data is currently not being observed anymore. However, I also need to make the point very clear. You see those lines here where the subsidence rate is very, very high. Those are the sites where water vapor is being extracted. So, of course, we still see the pumping sites where we extract water vapor at the CanGen sites, but we don't see a larger scale signal necessarily anymore. In fact, if we look only at the last year between 2024 and 2025, we actually see that there is uplift occurring in this area. So I'm skipping over the east-west profile because I just wanted to point out that we are working closely with the KenGen team to install, or we have installed a GNSS network that is active since December 2023, and we have been adding a couple of stations. And we are monitoring sites at the new geothermal stations. So those black crosses indicate the locations of our GNSS sites, and we are using these sites to validate our InSAR data. So, we heard in the first presentation that the GNSS network is very sparse. Yes, that is, of course, the case in this area. So that local network helps us to better understand the deformation of the Olkaria field. Let me wrap it up here by giving a few points of conclusion. The persistent scatter InSAR time series suggests that subsidence rates across the Olkaria geothermal field have slowed down in the past 3 years. So that's a regional signal. So there have been some rate changes that we observe. The spatial line of sight pattern of Sentinel-1 and TerraSAR-X indicates strong impact on local subsidence at water extraction sites. So those were the red dots that I was showing earlier. So we can see very clearly where we have pumping sites and where a lot of excess water is being extracted, and the surface is responding by an increased subsidence rate. Just as a last point, even so I have not been showing you the data due to the time constraint here, the GNSS and TerraSAR-X measurement of the past year report similar rates as the Sentinel-1 measurement. So we are confident that different data sources point to the same rates, and we tend to believe them. Thank you. Thank you very much.
Yeah, thank you very much, Bodo, for that presentation. So we can open it up for some questions. There's a couple of minutes. Yeah, is it Kathy? Did I see your hand up or down?
I was just clapping, but I was wondering if there's any explanation as to why the subsidence rates have slowed down recently.
Well, there is more geophysical data available that sits with KenGen that have looked at this. What I presented today is really only the surface structure, so I can only speculate using these data. But looking at the Longonot volcano to the east and looking at the larger spatial pattern, we are assuming that these are magma bodies that change their size and heat structure within a couple of years that cause these subsidence and uplift signals.
So it's tectonic rather than any change in the way that the power plant is operating?
Well, I don't know if I would say that. I mean, we can clearly see that there is a surface signal of the extraction of water. We see the red dots. The question is, how large scale is that signal? Currently, what we see a lot of ups and downs on Longonot as well. And there is no water extraction occurring and no energy production. And in fact, the steepest, I have not shown this, but the steepest subsidence rate in the Olkaria geothermal field is to the west of the field where there is no active extraction occurring. So I think it's a complex problem that where many different things interact with each other and that create a signal that we then end up measuring.
Okay, thank you.
Okay, Karen?
Yes, hello. Yeah, I guess my question was actually very similar. To what extent, hypothetically, if there was a magmatic intrusion at some point, to what extent it would be possible to distinguish that at these high-resolution data, and what the interaction with Longonot might be, but I guess you already partially partially answer that.
I think what we are in the process of doing that, also with colleagues at the University of Twente that look at reservoir modeling. So that surface radar interferometry data that I just presented is just a small piece of many other data sets that exist that probably better help you to understand what's happening in the subsurface. But at least from what we currently see in the newest time series that we have, we see an uplift in the last 2 years. So that initial subsidence that was reported is there, but it stopped.
Okay, Tina Newman, there's also an answer by Dr. Menda on the chat, I think relating to the role of re-injection in slowing down the subsidence observed in Olkaria. You can just check that. Tina Newman?
Yeah, so very interesting talk and great work. So I was wondering, in your method, you explained that you select certain wavelengths, certain signals. How does that can you just over the whole signal you get, is it reliable, or is this uncertainty different depending on what you select?
Well, I use the same radar wavelength. So the Sentinel-1 is a C-band sensor. The TerraSAR X is an X-band sensor. So these are two different frequencies. But I think you're referring to the difference of distributed scatterers and persistent scatterers.
Sorry,
so
yeah.
my apologies that I didn't introduce that properly. So the persistent scatterer is a way of only looking at a single point where you have a strong reflection. That's often used in urban environments where you have buildings and houses that create a very strong reflective signals, but it also works in outcrops where you have a bedrock outcropping, which we do in the Olkaria area. Whereas the distributed scatterer is being used by just averaging over many pixels. So you just increase the area, you make the area that you're looking at larger, and then you're averaging over that signal to get the phase out. That works well in vegetation-free areas, but if we have vegetation or soil moisture, we can introduce a bias that makes it more complicated to interpret that signal.
That makes it more clear. And in the first method, you kind of assume that your reference is constant, so it doesn't change the backscatter over time.
Exactly. So if I'm using the distributed scatterers, I'm averaging out to maintain still a good signal. In the persistent scatterers, I'm only choosing the points where the backscatter remains the same over a longer period of time. Yes.
Okay, very interesting.